Hi everyone. In the last few classes, we discussed about bounded operators. Today, we will discuss some more important properties of bounded operators. So, if T is bounded, we have defined that norm of T is supreme of norm Tx by norm x. X is in the Hilbert space H1 and x is non-zero. In fact, we can also say that norm of Tx is less than norm T times norm x for every x in H1. In the earlier equation, we have assumed that x is non-zero, but in the latter equation, even it is also true for x equal to 0. Hence, we can conclude that this is true for all x in H1. So, in order to find the norm of the operator, what we have done was we found some k. So, the first step to find norm, we found out that show that there exists some k such that norm Tx less than or equal to k times norm x for every x in H1. So here we can put norm 1, here norm 2, depending on the Hilbert space. This is 2, this is 1. Okay, this is the first step, and show that. So find some unit vector, find, let us say, x0 in H1 with norm x0 is 1 such that norm Tx0 is exactly k. Then in that case we can conclude that so these two steps imply that norm T equal to k. And we also seen one example where this is not possible, finding a unit vector x0 such that norm of Tx0 is exactly k. It need not be possible, but in that case we found a sequence of unit vectors which approximate the given operator, and using that we have shown that k is exactly norm T. Okay, so this is the way to find norm of an operator. Now let us look at one example of an operator which is not bounded. So yeah, let us try to see few examples. Let us take x to be c dash 0 1, set of all functions from closed interval 0 1 into c. F dash is continuous on 0 1. That means f dash exists and it is continuous. And define d from x to c01 by d of f is f dash, where f dash is the derivative of f. Okay, so we can check that. Let us take phi n of t as t power n, and so n is in n, so we are defining phi n t like this. So we can easily show that here we always take sup norm. So norm of phi n, sup norm is 1 for all n, and if you look at norm of d phi n, On C01 also we take the supremum norm. This is nothing but subnorm of n phi n minus 1, because phi n dash is nothing but n times t power n minus 1, that is phi n minus 1. This is nothing but n times subnorm of phi n minus 1, and we know that this is 1, so this is n. So if you take this set B as phi n, this is bounded in X, but D of B is not bounded in C0. So we got a bounded set which is mapped to an unbounded set by this operator f going to f dash. So hence we can conclude that therefore D is not bounded. Okay, so if you observe the domain of this operator is C dash 01, which is not a Hilbert space, and the codomain also we have taken with respect to subnorm. C01 with subnorm is not a even inner product space. So this example is between two normal linear spaces. Let us look at one more example on Hilbert space. So let us take a set D as set of all sequences in L2, complex sequences. L2 means L2 of natural numbers, such that summation n equal to 1 to infinity n xn square is finite. Now this is a subset of L2. We can easily show that it is a subspace. So easy to check that D is a subspace. We can ask whether D contains any non-zero elements. Clearly 0 is an element of D, but can D contain any other elements of L2? So we can look at the standard orthonormal basis of L2. Okay, so for example E1 is 1 0 0. Okay, now this, if you take E1, that is an element of L2, but that is in D also. Because if you look at summation n equal to 1 to infinity n into xn, now mod xn square. So first element is 1, so mod xn is 1 anyway. So we can conclude that this is finite. In fact, we can show that any en is in D. So we can also show that similarly C00 is in D. We know the space C00. Now we know that C00 is dense in L2. With respect to L2 now, this is dense in L2. Okay, so that means this is a dense subspace. Now define an operator T from D into L2. So clearly D is not a Hilbert space, right? Because D is dense subspace of L2. If D is a Hilbert space, it has to be a closed subspace, which is again dense and closed implies that it has to the full space. So, but this is not a full space because you can always find element in L2 which is not in D. For example, you take 1, 1 by 2, 1 by 3, this element 1, 1 by 2, 1 by 3, so on. This is in L2, but it is not in D. Because when you look at summation n equal to 1 to infinity n into xn, that will be 1. So if you take the sum, it is not finite. So this is a proper dense subspace of L2. So we are defining a linear operator by T of x1, x2, so on. This is x1, 2x2, 3x3, so on, for every xn is in L2. Sorry, for every xn in D, because whenever xn is in D, then the right hand side is an element of L2. So this definition makes sense. So we can easily check that T is linear, but it is not bounded. If you look at T of En, where En is the standard orthogonal base element of L2, this is nothing but n times En for every n in N. So let me recall, En is 0, 0, 0, so on 1 in the nth place, and remaining are 0. So here if you take again B equal to the set En, n in N, this is bounded in L2. In fact, it is bounded subset of D, but T of B is not bounded in L2. Hence, this operator cannot be bounded. So this is an example of an unbounded operator. So the conclusion is T is unbounded. But this operator has one important nice property, namely it's a closed operator. So next we discuss about the meaning of a closed operator. So before discussing that, we need to know something about direct sum of Hilbert spaces. So let us look at that part. Okay, suppose we have two Hilbert spaces. Let H1, H2 be Hilbert spaces. Over the complex field C. Then we define their direct sum as H1, H2. So here if you take any element X as X1, X2 and Y as Y1, Y2 in H, then we define X plus Y as component wise addition, X1 plus X2, sorry, X1 plus Y1 comma X2 plus Y2, and alpha X as usual, this is alpha X1 comma alpha X2, where alpha is a complex number. With respect to these two operations, we can check that this H is a vector space, which is a complex vector space. You want to make this to be an inner product space, in fact a Hilbert space. Okay, so let us define a new inner product xy, where x is this and y is this. This is inner product of x1 with y1, and x1, x2 or x1 and x1, y1 are coming from h1. So this is the inner product in h1, and this is inner product in h2. Okay, the corresponding norm or induced norm, this is nothing but take y equal to x, you will get norm x1 square in the Hilbert space h1, and this is norm x2 square, and this is the norm in the second Hilbert space. Okay, and if you want to take norm, this is nothing but, this is similar to the Euclidean norm on R2 or C2. So this is a generalization of C direct sum C. Now with respect to this inner product, we can check that actually H with respect to this new inner product is an inner product space. We can actually very well start H1, H2 to be inner product spaces and show that S is an inner product space, but we started with Hilbert spaces. So because H1 and H2 are Hilbert space, we can show that also it's a Hilbert space. The other way is also true. If you define H this way, you start with two inner product spaces H1 and H2, define H in this way, the way we have defined, and if you define the inner product in this way, we can, if this is Hilbert space, we can automatically show that H1 and H2 to be Hilbert spaces. Okay, so we found a Hilbert space from two different Hilbert spaces. In fact, we can take the direct sum of finitely many Hilbert spaces in the same way, and in fact countably many and uncountably many also. But when we go for infinitely many Hilbert spaces, we have to put a condition that summation norm xi square is finite. This is similar to the definition of L2 norm. So this in fact generalizes the L2 norm definition of Hilbert's L2 definition. Okay, L2 space. Okay, now why we want to discuss about these direct sums. So maybe we can easily look at we can easily show that this H1 can be embedded in H2 as follows. And H2 can be embedded in 0 direct sum with H2. This is exactly subset of. You can compare this with x-axis and y-axis and R2. Okay. Now we want to define graph of an operator, which is a generalization of graph of a function. So let us quickly recall. So if f is a function from x to y, then graph of f is set of all x comma fx, where x is coming from x. This is inverse subset of x cross y, right? Here also we have taken h1 cross h2, and with respect to these operations we are calling as h1 direct sum h2. Okay, now the same way, if T is a linear map, from, in fact we don't need to take this part, need not be defined on a Hilbert space. If T from D to, let us say H2, where D is a subspace of H1, a subspace, then suppose this is linear, then graph of T is set of all x comma tx, where x is coming from D. Here D is known as the domain of T. So domain is nothing but set of all points in H1, where set of all x in H1 where Tx is well defined. Okay, that is called maximal domain also. So sometimes this is also written as so D is written as D of T to say that it's a domain of T. Okay, now this is a subset of D cross H2, and again D is subset of H1. So here instead of D cross H2 we can always say that it is D direct sum H2, this is H1 direct sum H2. So G of T we can easily show that to be a subspace of this direct sum. So G of T is a subspace of H1 direct sum H2. Okay, that is because T is the linear map. Okay, now what exactly we want to show is that if T is continuous map or T is a boundary linear map, that means if T is defined from H1 into H2, then graph of T we can show to be a closed subspace of H1 direct sum H2. Exercise: if T is a bounded operator from H1 into H2, then we can show that graph of T is closed. It's a closed subspace of H1 cross H2. Now if you see operators like T, whatever we have defined earlier, which are defined on a subspace of H1 instead of defined on the full space, then also we can define the graph of the operator, and then graph of T is a subset of H1 direct sum H2, and it may be possible that graph of T is closed even though T is not bounded or T is not continuous. So such a map we call as a closed operator. Okay, so definition: let T is a map defined on dt and taking values in H2. dt is a subspace of H1 linear, then T is called closed if graph of T is closed. Let us see what is the meaning of graph of T is closed. So okay, suppose graph of T is closed. Here closure is with respect to the norm induced from the inner product of H1 direct sum H2. So because this is subset of H1 direct sum H2, that means let us take, if you take two elements yz and the pair yz in GT closure, then actually we can say that there exists a sequence xn and yn from GT closure, because elements of we have to approximate yz from this one. Okay, so we can actually, so there exists a sequence yn zn from GT such that yz is limit of yn zn. Now yn zn is an element of GT, but GT elements are of the form x comma tx, so it should be yn comma tyn only. So this is yn tyn. So since zn is tyn, now from this we can conclude that yn converges to y and tyn converges to z. So this we can easily show that whenever we have a sequence converging in H1 direct sum H2, the corresponding components converges in H1 and H2 respectively. So using that we can conclude that yn converges to y and tyn converges to z. Now but so we know that gt closure is nothing but gt, so we can say that this y comma z is also in gt. Right. So this implies that, so that is, we can say that z is of the form ty, so z equal to ty for some y has to come from domain of t. That means automatically we are concluding that this y is in domain of t and z is nothing but ty. So it cannot be for some y, so that here we can conclude that is y is in domain of t and ty is exactly z. So let us try to summarize what we have proved. If graph of t is closed, that means when t is a closed operator, and if xn is if yn is any sequence in yn zn is a sequence in graph of t, then we were able to show that this way, that y is in domain of t and ty is z. So we can also say that graph of t is closed implies if xn is any sequence in domain of t such that xn converges to x, and earlier we have seen that zn is nothing but yn, so that is nothing but, sorry, zn is nothing but tyn, so here txn converges to y implies x is in domain of t and tx is in, so t is closed implies this condition. In fact the other way is also true. We can easily check the other way, that whenever we have sequence xn converges to x and txn converges to y, implies x is in domain of t and tx equal to y, when we can easily show that graph of t is closed. So what we have concluded is that t is a closed operator if and only if this condition is satisfied. Okay, so now we want to ask what is the difference between a closed operator and a bounded operator. Yeah, so the difference is given by the closed graph theorem, which we already know. If t from d of t into h2 is a closed operator with domain of t equal to h1, then t must be bounded. So here we assume that t already a linear operator, because when we discussed about closed operator, we assume that it's a linear map. Yeah, of course without assuming linearity also we can define closeness, but here we assume that t is a linear map, and if graph of t is closed, we call it to be a closed linear operator. So this actually, the closed graph theorem says that whenever t is a closed linear operator whose domain is full space, then automatically it's a bounded operator. That means the difference between the closed operator and bounded operator is the domain. If the domain is the full space and it's a closed, then it's bounded. That means for a bounded operator, domain is the full space. We always assume that domain is full space. Now one can ask the converse. What happens if t is a bounded operator? Can we say that it's a closed? So if t is a map between h1 and h2, if it is bounded, we have already seen that graph of t is closed, since it is closed. But when t is defined on a proper subspace, let us say t is defined on D and taking values in h2, and if t is bounded, then t need not be closed. So we can actually find examples for that. Next we study some more important properties of bounded operators. Let us Look at Hilbert space HB Hilbert space. Let us fix some element. Then we can define a functional based on or depending on x from h to c by phi suffix x at y is inner product y with x for every y in h. Then we can easily show that phi suffix x is linear, and we have mod phi x at y is less than or equal to norm y norm x by the Cauchy's coarse inequality. So from this we can conclude that norm of phi x is less than or equal to norm of x. That means phi x is linear, and we can also show that by choosing appropriate vector y. So y equal to x by norm x, if you look at, then we can phi x at y is exactly norm x square by norm x, so this is norm x. Okay, of course you have to start with a non-zero functional phi suffix x, and x is non-zero. Of course when x is 0, phi suffix x becomes 0. In that case also the same result holds true. So in other words, we can conclude that, so the conclusion is the following: norm of x is nothing but norm phi suffix x. This is supreme of modulus of inner product y with x, where y is coming from h1 h and y non-zero. So here we can actually take norm y equal to 1. So in other words, we can actually write norm of an element in Hilbert space to be supreme of this quantity in terms of inner product. Now the same thing, if T is a bounded operator, let us take T to be a bounded operator from h1 into h2, then we know that norm of Tx, norm of T can be expressed in terms of norm of Tx. So norm of T is supreme of norm Tx in the second Hilbert space, where x is in h1 with norm x equal to 1. Now Tx is an element of h2. Now apply Tx, apply the earlier formula whatever we got for x for Tx. So by the earlier formula, let us call this as star. So we can say that by star we can write norm of Tx in the Hilbert space h2. This is supreme of modulus of inner product Tx with y, where y is in h2 and norm y equal to 1. Okay, so let us try to look at these two equations. Let us say this is 1 and this is 2. Then from 1 and 2 we can conclude that norm of T is exactly supreme of modulus of inner product Tx with y, where x is coming from h1 with norm x is 1 and y is coming from h2 with norm y equal to 1. So we can express norm of an operator which is defined between two Hilbert space H1 and H2 in this way. So this is one more formula of norm of the operator which is given in terms of the corresponding inner product. Okay. Now as we have seen earlier, given any x in H, we can create a functional in this way. Now the converse is the ridge representation theorem that we have already discussed in the review of Hilbert spaces. So by the let me quickly recall. If phi is in H star, where H is a Hilbert space, implies of course phi is non-zero. There exists unique element x in H such that phi of y is inner product y with x for every y in H. That means every bounded linear functional on Hilbert space is given by this one. It is represented by a unique vector. Now using this result, we can actually associate a new operator in a unique way with the given bounded operator. So let us try to look at that part. Let us start with a bounded operator defined between two different Hilbert spaces H1 and H2 and fix one vector y in H2. Now define a functional depending on y in this way from H1 into C by phi y at x is nothing but inner product Tx with y. This is for every x in H1. Phi y is defined on H1 which sends x into inner product Tx with y. Now since T is linear, we can show that this easily to verify that phi suffix y is linear as T is linear. The next question we can ask is that is it bounded or not. So for that let us look at modulus phi y at x is modulus inner product Tx with y. So this is inner product in second Hilbert space, let us say 2, but it's not required also. So this is less than or equal to norm Tx multiplied by norm y. So this is 2 norm, and this is less than or equal to norm T into norm x in the Hilbert space 1, and this is in the Hilbert space 2. So this implies that phi is bounded, phi y is bounded, and not only that, norm of phi y is less than or equal to norm T into norm y. So this is a finite quantity. So phi y is a bounded operator with this bound as a norm. Okay, now we can apply Riesz theorem for this particular functional phi suffix y. So by the Riesz representation theorem, there exists a unique let us say x or z in H1 such that phi y at x is inner product of x with z. This is for every x in H1. Phi suffix y at x equal to inner product Tx with y, but by the Riesz theorem this can be written as, and not only that, norm of phi suffix y and norm of z both are same. Okay, so let us quickly summarize what we have done. We have started with a fixed vector y in H2 we have started with a fixed vector y in H2, and we got a unique vector z in H1 which satisfies this condition. Let us quickly rewrite what is the condition. So earlier condition was inner product Tx with y, this is second Hilbert space, and this is nothing but by this relation, let me call this is 1. So by 1, so this is inner product x with z for every x in H1 and for every y in H2. So the reason is that y we have fixed earlier, but this process can be done for every y, and you can keep in mind that this z also depends on y all the time. Okay, so z suffix y. So given y in H2, we got one vector z, and z has the property that z satisfies this inequality or this equality equation 2, where y and z satisfy 2. That means given a y in H2, there exists a unique z in H1 such that inner product Tx with y equal to inner product x with z. That means we can actually define a map. So now define a map S from H2 to H2, H2 to H1, sending y into z, where z satisfy 2. Okay, and this that means we can replace z by sy, that is inner product Tx with y is inner product x with sy, because sy is nothing but z. So we got a linear we got a map from H2 to H1. It is an operator. Now we want to say that is it linear. I mean, we can ask the question that is S linear. So these are the following questions we can easily ask. Immediately we can ask the following question, that is S linear, bounded, what is norm of S, how it depends on the properties of T. So these are the questions we can ask immediately. Let us try to look at one by one. It is easy to show that S is linear. So verify, because of the linearity property of the inner product in the first variable and the map T is linear, we can conclude that S is linear. Now is S bounded? Yeah, we can actually show that S is bounded. So when okay, so it is enough to show that norm of S is a finite quantity. So by definition, earlier we have already proved this is supreme of modulus of inner product sy x, where y is coming from H2, norm y equal to 1, x is in H1, norm x is 1. So this is nothing but supreme of. Now look at the relation between syx and txy. So this is ytx norm y is 1, x is in H1. Now we can write supreme of this, we can write as supreme of mod inner product Tx with y, where x is in H1 with norm x is 1, y is in H2, norm y is 1. And we know that this is by the earlier formula, that this is exactly norm T. So this says that S is a bounded operator and norm of S and norm of T are same. Okay, so this is a linear map which is bounded. Now the question arises, is it a unique operator? First of all, we have not checked that it is a well defined operator. The question is that is yes well defined. In other words, can this S be a unique operator satisfying those properties? This can be seen easily. Suppose if S tilde is another operator, satisfying inner product Tx with Y is inner product X with S tilde Y for every X in H1 and for every Y in H2, then we can say that X Sy and X S tilde Y are same. In fact, the same for every X in H1 and for every Y in H2. Now from this we can conclude that inner product of X with S minus S tilde Y is 0 for every X in H1. So this implies, and for every Y in H2, this implies Sy equal to S tilde Y for every Y in H2. So this implies S equal to S tilde. That means the map is well defined and such a map is unique. What is the meaning of such a map? That it satisfies inner product X with Y equal to inner product X with Sy. So in fact here this is in the inner product, first Hilbert space. Okay, so such a map we call as adjoint of this unique map we call as adjoint of T. So the unique map or operator S is called the adjoint of the operator T, and it is denoted by T star. In other words, we can write S equal to T star in the earlier equation. So we can say that T and T star are connected by the following equation. Inner product Tx with Y is nothing but inner product X with T star Y for every X in H1 for every Y in H2. Note that the inner product on the left hand side is in the second Hilbert space and the inner product on the right hand side is in the first Hilbert space. Okay, so this is called the adjoint of the operator, and one can ask the question why this is called adjoint. Is it anyway connected with the adjoint of a 2 by 2 matrix or n n by n matrix? In fact, this is the case. We will be seeing at a later stage that this adjoint is an exact generalization of adjoint of a complex matrix. So let us see with a simple example. Let us start with A, B, C, D, which are complex numbers. Look at A equal to A, B, C. Look at this matrix, 2 by 2 matrix. Define an operator T from C to C2 by T of xy as A of xy. This is nothing but ax plus by cx plus dy. This is for every xy in C. Now let us try to find T star and see whether we can connect this with the adjoint of a matrix. Okay, so if you look at the equation satisfy T and T star, this equation, if you want to find what is T star, you have to look at inner product Tx with Y and we should be able to write that as inner product of x with t star y. Then easily we can find out what is t star. So let us do the same here also. So let us take another vector zw in C2 and consider txy inner product with zw. Now we want to write this as inner product xy with something. That something become t star. So if you look at txy, this is ax plus by comma cx plus dy, and this is zw and inner product, and this is nothing but this is inner product in the same both sides we are looking at C2 only, so we don't have to write subscripts for the inner product. So here this inner product is ax plus by z bar plus cx plus dy w bar. This is nothing but ax z bar by z bar plus cx w bar plus dy w bar. Now we want to write this as inner product of xy with something. So let us try to take x out here. This is a z bar plus here in this from the other term, this is plus c w bar plus, if you look at y, b z bar plus d w bar. So this we can write as inner product of the tuple xy with bar of the remaining two components, that is a z bar plus c w bar and b z bar plus d w bar. So that we have to take as bar. So you will get a bar z plus c bar w comma b bar z plus d bar w. So this we can write as inner product of x with y. So this we can write in terms of matrix. This is a bar z, a bar c bar, b bar d bar zw. Of course we can represent zw as the column matrix zw. So this is nothing but inner product x with y. This is t star of zw. So that means t star of zw is nothing but, if you look at the matrix a bar c bar b bar d bar, that is exactly adjoint of a star. So we can say that this is a star zw. That means if t of xy is a of xy, then t star of zw is nothing but a star of zw. In other words, if the operator t is given by the matrix A, then the operator t star is given by the operator A star, that is matrix A star, that is adjoint of A. So this is a connection between adjoint of a matrix and adjoint of an operator. Adjoint of an operator is generalization of adjoint of a matrix. Okay, let us look at one more simplest example. Let us look at the right shift operator. R of x1, x2, x3, so on, 0, x1, x2 for all xn in L2. So let us take, we want to find what is the adjoint of R. So let us take x as x1, x2, so on, and y as y1, y2, y3, so on. Both are in L2. We want to find what is adjoint of R. So let us look at inner product of Rx with Y and try to write this as inner product of X with some operator that we call as R star Y. That is the idea. So let us look at this one. Rx is nothing but 0, x1, x2, x3, so on, inner product with y1, y2, y3, so on. This is x1, y2 bar plus x2, y3 bar, so on. So this we can write as x1, x2, x3, so on, inner product with y2, y3, y4, so on. So we can conclude that R star of Y, where Y is y1, y2, y3, so on, we can write this as y2, y3, y4 for all. So this is exactly the left shift operator, this L of. Okay. Now we can ask the question, if you find out adjoint of left shift operator, what will happen? So the question is, what is L star? In fact, surprisingly we can show that L star is again exactly R. So in general, check that the right shift operator, in general, if T is a bounded operator, then T star and star is exactly T. Okay. So these are a few examples. In the next class, we'll be discussing about how to compute adjoint of an operator with more examples and some more interesting properties of adjoint of an operator. We'll stop here. Thank you.